The functions of the landing gear are, firstly, to provide a means of manoeuvring the aircraft on the ground. Secondly, to support the aircraft at a convenient height, to give clearance for propellers and flaps, etc. And thirdly, to absorb the kinetic energy of landing. Once airborne, the landing gear serves no useful purpose and is dead weight. It would be ideal to replace it with some ground-based equipment which detached on takeoff, as with this Messerschmitt Comet. But while it's possible to achieve manoeuvring and support for the aircraft with ground-based equipment, no satisfactory alternative exists for absorbing the kinetic energy of landing and providing a means of controlling deceleration. For this reason, a vast amount of research has gone into the design of undercarriage units in order to reduce their weight and their stowed volume when retracted. With slow, light aircraft and some larger aircraft on which simplicity is of prime importance, a non-retractable landing gear is often fitted. The reduced performance caused by the drag of the landing gear during flight is offset by its simplicity, its reduced maintenance, and also its low initial cost. With higher performance aircraft, drag becomes progressively more important, and the landing gear is retracted into the wings or fuselage during flight. There are, however, penalties of increased weight, greater complication, and additional maintenance. There are three main types of fixed landing gear: those which have a spring steel leg, those which employ rubber cord to absorb shocks, and those which have an oleopneumatic strut to absorb shocks. Exceptions include aircraft with rubber in compression, spring coil, and liquid spring struts. Spring steel legs are usually employed at the main undercarriage positions. The leg consists of a tube or strip of tapered spring steel, the upper end being attached by bolts to the fuselage, and the lower end terminating in an axle on which the wheel and brake are assembled. When rubber cord is used as a shock absorber, the undercarriage is usually in the form of tubular struts, designed and installed so that the landing force is directed against a number of turns of rubber in the form of a grommet or loop. Some fixed main undercarriages, and most fixed nose undercarriages, are fitted with an oleopneumatic shock absorber strut. The design of individual struts varies considerably, but one point worthy of consideration is the fitting of spats to oleopneumatic struts. Spats are an aerodynamic fairing which may be required to minimize the drag of the landing gear structure. One drawback to their use is the problem of them picking up mud when landing or taking off from grass airfields. This can add considerably to the weight of the aircraft and may affect take-off performance. To avoid this eventuality, if any mud has been picked up, the spats must be removed, cleaned, and replaced before the next takeoff. The nose undercarriage is usually a lighter structure than the main gear units, since it carries less weight and is usually subject only to direct compression loads. The nose wheel must be able to caster freely. Castering is the ability of the nose wheel to turn to either side in response to differential braking. A method of steering is required to enable the pilot to maneuver the aircraft safely on the ground. Early methods involved the use of differential braking, but today the nose wheel steering of most light aircraft is controlled by the operation of the rudder pedals, which are connected to the nose wheel by control rods or cables. Due to the flexibility of tyre sidewalls, an unstable rapid sinusoidal oscillation or vibration known as shimmy can be induced into the steerable parts of the undercarriage. Excessive shimmy, especially at high speeds, can set up vibrations throughout the aircraft and can be dangerous. Worn wheel bearings and uneven tyre pressures can both increase the tendency of the wheels to shimmy. Shimmy can be reduced in several ways. For instance, by fitting a shimmy damper, or by having heavy self-centering springs fitted in the nose wheel steering control rod run. Some larger aircraft have double nose wheels fitted, while twin contact wheels have also been found to be effective in minimizing tail wheel shimmy. An increasing number of light aircraft are fitted with a retractable landing gear, for the purpose of improving aircraft performance. Retraction is normally effected by a hydraulic system, but pneumatic or electrical systems are also used. In some instances, power is used for retraction only, extension being effected by gravity and the slipstream. Retractable landing gear is also provided with mechanical locks to ensure that each undercarriage is locked securely in the retracted and extended positions, devices to indicate to the crew the position of each undercarriage, and a means by which the landing gear can be extended in the event of a failure of the power source. In addition, a system is provided to prevent retraction of the landing gear with the aircraft on the ground, and to guard against landing with the landing gear retracted. Undercarriage wells are normally sealed by doors for aerodynamic reasons. Aircraft wheels are fitted with pneumatic tyres. These can consist of both a rubber inner tube and an outer cover. The tube contains compressed air which absorbs shock and supports the weight of the aircraft, while the cover restrains and protects the tube from damage, maintains the shape of the tyre, transmits braking effort, and provides a wearing surface. The tyre cover consists of a casing made of rubber, which is reinforced with plies of cotton, rayon, or nylon cords. The cords are not woven, but arranged parallel in single layers and held together by a thin film of rubber, which prevents cords of adjacent plies from cutting one another as the tyre flexes in use. During construction of the cover, the plies are fitted in pairs. Each pair is termed a pocket, which is set so that the cords of adjacent plies are at 90 degrees to one another. This is called cross-ply. The tyre manufacturers give each tyre a ply rating. This rating doesn't relate directly to the number of plies in the tyre, but is instead the index of the strength of the tyre. These special plies are termed breaker strips, to absorb and distribute load shocks, and also to protect the casing from concussion damage. Narrow plies embedded in thick layers of rubber are situated between the casing and the tread. The casing is retained on the rim of the wheel by interlocking the plies around inextensible steel wire coils to form ply overlaps. This portion of the cover is known as the bead. To assist you, should you ever need to describe the cover, it's divided into regions or sections as illustrated here. The tread of the tyre is situated on the crown and shoulder section. The sidewall allows the tyre to be flexible, and the bead is seated inside the flange of the wheel. Note that the term tread is applied irrespective of whether the rubber is plain and smooth or moulded on a block pattern. The most popular tread pattern is that termed ribbed. It's formed from circumferential grooves around the tyre. The size of a tyre is marked on its sidewall and includes the outside diameter, the inside diameter and width of the tyre, all in inches. The ply rating, the index of the tyre's strength, is also marked on the sidewall. Normally it's shown as an abbreviation, for instance 16PR, but occasionally it's shown in full as 16 ply rating. The speed rating of the tyre, the maximum speed for which it's designed, is imprinted on a panel on the sidewall of some high-speed tyres. The rating takes account of pressure altitude, ambient temperature and wind component, enabling the maximum takeoff weight the tyres can sustain to be calculated. Green or grey dots painted on the sidewall of the tyre indicate the position of the all vents. All vents prevent pressure being trapped between the plies, which would cause disruption of the tyre carcass if it was exposed to the low pressures experienced during high-altitude flight. A red dot or triangle indicates the lightest part of the tyre. If this is placed opposite the valve during tyre fitting, then it assists in balancing the wheel assembly. Tyres must be protected from excessive heat, dampness, bright sunlight, contact with oil, fuel, and hydraulic fluid. All of these have a harmful effect on rubber. Covers should be placed over the tyres when the aircraft is to be parked for any length of time, or during the periods when oil, fuel, cooling or hydraulic systems are being drained or replenished. Any fluid inadvertently spilt or allowed to drip onto a tyre must be wiped off immediately.